let's start with linear regression. So as per you said that you know what is linear regression, right? Okay, so let's look into this first. When we say machine learning types, it is basically divided into four, right? One is about supervised, second one unsupervised, semi-supervised, and reinforcement learning. So most of the times we will be focusing on supervised and unsupervised learning only. When we say supervised learning, continuous target variable or categorical target variable. Target variable means nothing but output, okay? So if the target variable is an categorical data, then it is a classification. If it is a continuous, then it is regression. So one example is also given, like housing price prediction is an example for regression, and medical imaging is an example for classification, right? And in unsupervised learning, there is no target variable, right? And then there could be two cases. One is about clustering and the other one is about association. Clustering means an example is customer segmentation. Association is market basket analysis that we will be seeing deeply, right? Okay, so the next one is about semi-supervised learning. Again, here it is about categorical target variable, like it is classification and clustering. So one is about, if it is classification, text classification. Basically, it comes into like text kind of data. And for clustering, an example is given like lane finding on GPS data, right? And this reinforcement learning, actually these two we are not covering basically. So reinforcement learning, it is about categorical target variable, and there could be another case like target variable not available. So basically reinforcement learning works based upon rewards and punishments, right? So if it is a classification, then example is given as optimized marketing, and if target variable is not available, then an example is given that driverless cars. Right. So let us try to understand what is linear regression. Recommendation systems generally falls under AI. Right. Okay. Okay, fine. So, okay, fine. Yeah. So let's see what linear regression is. We are not going to we are not going to the detail of it. Just let me tell you what is what, right? So I think you know the equation y is equal to mx plus c. So that is being written as y is equal to a plus bx, whatever it is. This x is predictor, which is the what variable it is? It is independent variable. Hope I said about independent and dependent variables to you, right? What are independent and what is dependent variable? There could be only one dependent variable and there could be multiple independent variables, right? You are familiar with that. So b is nothing but coefficient of x, and a is intercept, right? So if you feel that it is confusing, just you study always as y is equal to mx plus c. Y is the predicted value and m is the coefficient of x, and x is the independent variable, and c is the intercept. Right now look at this, like here it is a picture for time and stock price, right? And here this is about independent variable and dependent variable, and a line is being drawn. So basically, what is the aim of building a linear regression model, right? So there are points for x, and basically what we try to do is we are trying to find a best fit line, right? We are trying to find a best fit line in the sense like these are the data, so we can draw any number of lines, right? We can draw any number of lines, but which is the best line for this, that we do not know, right? So basically by building a model, we will be trying to identify which line is the best line that gives us a very good performance. So here there are some articles given, and since you have LMS access, you can just go through it, okay?
Linear regression is one of the most simple algorithms when it comes to machine learning. So, what is linear regression? By definition, linear regression is a statistical way of measuring the relationship between variables, such as time increases, so does cost. So, why does this matter? Well, simply put, you can predict the future. Let's use a real-life example. Let's say we're trying to predict the house price given the square footage of the home. In Seattle, Washington, according to Zillow, the average square footage value is $236. If we were to graph this, it will look like this. 1,000 square foot home equals $236,000. Well, what does a 2005 square foot home cost? Well, if we look at this graph, we could put a point there and determine that it's going to be roughly $473,180. Let's look at the math behind linear regression. The formula is quite simple. It is y equals mx plus b. Y is what we are trying to predict. M is the slope, or the $236 square footage value. X is the input, the value that we don't know, or in our case, the 2005 square foot value, square foot home. And B is the bias. Let's go ahead and implement this math equation. Well, y is the housing price. Since we are trying to predict the housing price, that is y. M, which is the slope, is going to be the 236 average square footage value. X is the square footage input, and B is going to be 0, or the bias is going to be 0. Let's go ahead and plug in the values given our example that we did earlier. We're going to plug in the 236 slope value. We're going to plug in the 0 bias value. And we're also going to plug in the 2005 square footage value. Now, if you calculate the right-hand side of the formula, it will equal out to be $473,180. And that is simple linear regression.
There are multiple videos given in this. So when you get time, you can go through it. Right. So let's try to understand the theory behind it. So you know that what is the M, what is C and all, right? So also the most important thing what we should know about is about a negative linear relationship or positive linear relationship, or whether there is no relationship, right? So you can look at this. We can say that it is positively correlated, negative correlated. So this could be linear, this could be curvilinear, and in case sometimes in cases, okay, so if it is like this, we can say that there is no relationship between the data at all, right? And y cap is equal to, okay, so let me tell you like what is this y cap and all, right? Okay, so look at this. So if you're not able to understand, please tell me. Okay, so now just look at this. This is x and y axis, and I have some data points. Just imagine that the data points are being plotted. Okay, step by step. First the axis is drawn. Now the data points are being plotted. Right. Now what is the next step? To find the line that best fit into that. Right, so this is being identified as the best fit line. Okay, let it be one line. Okay, just imagine that. Okay, so first time we are trying to do with this line. Okay, let it be line number 1. Right, now what is the value of y hat and y? This is what we are trying to do. So this equation, so there is an equation for this line, right? That is called as y hat. This is the predicted output. So y hat is equal to beta naught plus beta 1 x plus e. So that's about error. Okay, just you leave it off, beta naught plus beta 1 x, whatever it is. Right, so this is about the y hat. Okay, so for example, like in this case, okay, so what we are trying to find out is actually error. In this case, at least it is touching. So just leave it off. Come over here. Here you can see that this is the actual value. This is the actual value of x. But when you draw a line, we are getting, this is going to be the predicted value of this value, right? So this difference is called as the error. Here no error, and here there is an error. Now look at this, similarly this case. So what is the error over here? This distance is called as error. And similarly here there is error. Here there is error. Here no error. This is how the error is being calculated. So this is done for one line. Okay. Now just say that, okay, let's draw another line now. Right now, let's draw another line now. Then the next one could be of this line, for example, right? Okay, the next one could be of this line, right? Now in this case, here also there are errors. Basically, yes, there will be an error. Now we have another equation. Now here there will be one error, and again this distance will be an error, and again here will be an error, no error, and here there is an error, no error. So, for example, we are drawing two lines. See, basically, infinite lines can be drawn, right? Infinite lines can be drawn. For just an example, I'm taking only two lines, right? So, here we will be getting one error value, and second one we are getting an error value. So, which one will you consider as the best line? Number one or two? Which line will be can be considered as the best fit line? For both the lines, we have calculated error. Okay. So let me give the error also. For the first case, let it be around 0.84. And for the second case, the error is 0.23. So which line is the best fit line in this case? Exactly. The one with the minimum error second case. That is what we should understand, right? So whatever be the data points, any number of lines can be drawn into that. Which line is being considered as the best fit line? The line with the minimum error. Here we call it as residual. Okay, we call it as residual. The one with the minimum error is being considered as the best fit line. So that is what being explained over here. So here also it is saying about the error, right? So we have learned a new term which is called as error or residual. So how do we calculate this error actually? Y hat minus y the whole square. Y hat minus y the whole square. So let us take this point. What is this? This is actually y, right? This is actually this red point, that is actually y hat, right? The difference between the two, the whole square, right? This gives us the residual. So this is being done for all the values, right? Yi minus actually summation, right? Yi minus y hat the whole square, right? So this is what we will be doing. Is this part clear to you? And the one with the minimum error. So this is for line 1, right? Similarly, for all the lines, it is being calculated, and the line with the minimum error is being considered as the best fit line in linear regression. Why this is being squared? Otherwise, what will happen in case if we are... yeah, exactly. Right. You're right, Nico. Right. Fine. So is this part clear? Okay. The same point is being explained over here. And the additional point over here is about univariate linear regression and multivariate linear regression. Univariate linear regression means there is only one independent variable. If there are multiple independent variables, then it is multivariate linear regression, right? Now look at this. Okay, so we know how is m being calculated, right? How is the slope being done? Dy by dx, right? So that's being given over here. M is equal to dy by dx. And what is c over here? Where it intersects at the y-axis is called as c. Okay, so basically, so whatever it joins, okay, let it be 2. Now, can you tell me? Okay, here I'll write. This is 4 and this is 6. What is M and C in this case? If you are clear with that, we can go ahead. Yeah, B1 and U. So in this diagram, what is the value of M? What is the value of C? M is 0.5. What is C? Okay. What is C over here? Right. So this is what I'm asking. Okay. M is nothing but dy by dx, right? So what is the change in y over here? 3 minus 2 divided by 6 minus 4, right? So 1 by 2, which is equal to 0.5. So C means where does it intercept at the axis? So that is actually 1, right? So this is how M and C are being calculated. This you may be knowing it, right? Okay. Now look at this. You can see some new terms over here, right? R square, adjusted R square, and okay, this you leave it off, constant, that you leave it off, r square and adjusted r square. So what is this r square and adjusted r square? So I think you may be remembering that I have told that when we build a model, we should evaluate the model, right? Why should we evaluate the model? Because we should know whether the model is good or bad. So there will be metrics for each kind of learning. So for regression, we can check r square or adjusted r square. These two are the metrics to know the performance of the model. Now look at this here. You can see that r square is 0.898. Here adjusted r square is 0.888. So when we write the codes, we will be getting the answer for r square and adjusted r square. And based upon that, we can say that whether the model is good or bad, right? So basically it tells us about the variance, right? Okay. So we will be dealing with a data set, right? Okay. So what are the assumptions we consider in linear regression? So these four assumptions we should remember. The relationship is linear. The errors have the same variance. The errors are independent of each other. The errors are normally distributed. So these are the four assumptions we keep in linear regression. Okay. So in this case, now look at the first case. These are all fine. Okay, this could be the best fit line, but you can see an outlier over there, right? So there may be, we have to take a call whether we are going to drop the outlier or not, right? And also we should make a model which is robust to outlier, which means which is not sensitive to outliers. That is how we have to make a model, right? So that the model may be stable, right? Okay, so you can see over here, right, some examples are given like that, right? So here there is an outlier, and when the outlier is being removed, so when the outlier is being included, can you see this is how the line looks like? The Pearson correlation is found to be 0.4. When we remove the outlier, the correlation is found to be 0.7, and now you can see a better line, right? So comparatively to this, this is the better line, right? So that is the case we have to consider always. So how the outliers can be detected? Outliers can be detected with the help of z-scores, right? Right. So those things we will see, right? Now, this is what I said about the model evaluation. The model is being evaluated with the help of R square or adjusted R square, or there is another metric called as root mean square error. Basically, I prefer going with the RMSE, root mean square error. So what is the meaning of root mean square error? I told about residuals, right? Residual means I said like y hat minus y the whole square, right? Root mean square error means summation I equal to 1 to n 1 by n, right? This is what I said about residuals, and this is basically like square root of it, right? Root means square error, right? So this is a metric to identify the to understand the performance of the model, right? So that is being explained here. It is the standard deviation of the residuals. So residuals are nothing but predicted minus actual the whole square. Predicted minus actual value the whole square, right? So there are multiple videos given over here. So I don't think if we play everything, we may not get enough time to complete all the models, right? So that's why I'm not teaching that. Okay. So now let's see what are the libraries we need to do linear regression, right? So the first one is about, as usual, import a numpy as np, right? Import numpy as np. That will be the first one to do calculation, and then pandas as pd to deal with the data frame, because we have to read the data. Definitely the data is going to be in CSV, and then matplotlib, matplotlib and cborn also, in case cborn also definitely we need it, right? So that we can take it. And here they have taken from some other file. That is the reason they have written from py-data set import data, that we are not going to do now. And this is also related to See, I told you yesterday, you remember sklearn also has some data sets. In case if you get some time, you can work with the data sets that are readily available with sklearn, right? Otherwise, we can from sklearn, if you have sklearn, if you have installed sklearn, we will be able to build all the algorithms using sklearn library, right? Okay, so from sklearn import linear underscore model we do. And if we have to, I said that mean square error or R2 error, R2 score, all those are actually R square actually. So all these are called as metrics, right? So that is in sklearn.metrics. And so these are the important libraries we need when we do this linear regression, right? So when I show this, you may not be able to understand. I think better I will show you a code like how we can do with that. So basically how you want to know, like you want to also understand the codes, or you want to know how the algorithm works. How do you need basically? Can you tell me that? Because accordingly we can know.
We are just unsure about how to go about it. Can you just please explain it to us?
Sorry?
We are unsure about how to approach this.
Okay.
How it works, right?
Right. Okay, so just I have taken a simple example just to make you to understand how.
Lata,
Yeah.
so, sorry, I think the screen is not visible. We are still on the.
Yeah. I have not yet opened that.
Okay.
Okay, so the question what I asked was like, do you want to understand the codes also, or do you want to understand how the algorithm works? So basically, how do you want to know? Now you can see the screen, right? How algorithm works, right? So that is what we can do in this short period of time, right? Fine. Okay, so just I have taken a small algorithm, so just to make you to understand like how this concept basically works, right? Okay, so what I have taken is right. Okay, so let me show you that. Right. Okay, so what I have taken is I have taken a very small data set which is giving me information about area and price. Okay, so first step is that we have to import the libraries, and all the libraries are being imported like pandas, matplotlib, and I have not written numpy, I think. Yeah. Okay. So okay, so whatever libraries are needed, that has to be imported, and I have written another one. This may be new to you. sklearn dot linear underscore model import linear regression, right? So whatever model we execute, this is how we have to take that. Then what is the next step? We have to read the file. So that is actually book 2. So that's why I have taken that. And just I'm looking into my data. It is just saying about area and price. Okay, so I have taken a very small data set of 5,2 shape. Just I'll show you that how it is being working. Okay, then we will be dealing with a bigger data set. Okay, so what I have done is like in the axis I have taken area, and in the y axis I have taken price. Okay, and then I want to construct a scatter plot. So when I construct a scatter plot, this is how I got a graph. Okay, so now the question could be like, I can draw any number of lines over here, right? So that's what I try to say. This could be a line, this could be a line, this could be a line, this could be a line. So there could be any number of lines, but which line is the best fit line, right? That is the aim of the linear regression model, right? See, we are not going to do anything with this. We are not going to find out like which line is going to be the best line. So everything is being done behind the stage, right? So we won't be doing anything. So what we should understand over here is like I'm plotting and showing you. Now the aim is to okay, so what I have done, I am going to make a linear regression model, right? So this is the next step. So once we import the library, then we will be reading the file. This is the next important step actually. So in between we are doing few things, that's okay. But other than that, the next important step is that I'm writing that reg equal to linear regression, right? Reg equal to linear. So whatever may be the model, we have to write the model name. In case of I'm doing logistic regression, so what I should do is logistic, right? Logistic regression. Sorry. So that is how I have to write. Okay, logistic regression. And one more thing I want to tell you, right? So this is how we have to run it, right? So if you make it as logistic regression, here it is not defined because I have not yet imported logistic regression. That is the reason it is showing that. Since it is a linear regression model, I have to write it as linear regression, right? So basically, after reading, the mandatory step is that we should fit the model, right? How to fit the model? I'm writing reg or model or whatever you need, you can write it right here, equal to linear regression. Then I'm trying to fit with area, right, and price. So what happens over here? I want to know the coefficient, right? So the coefficient is being identified as 135 point. See, here we can get only one slope, right? So the answer is 135.7876 something I'm getting. So if I can get the intercept value also, right? So now if I want to find out the price for 3,300 square feet, how can I do that? Manually, I can do that 3,300 into, right, y equal to mx plus c, right? So 3,300 into 135.78767123 plus this is the c value, so that I can get the output of it. Have you done anything over here to find the best fit line or anything? We are not doing anything. It is being done by the library. We are not doing anything over here. But basically, yeah.
In the line 8, we can write df of area or df dot area as well, is it?
No, it will not work.
Okay.
Yeah, if you change anything, it will not work.
Okay, so x-axis should be in the bracket and
exactly. Right? Okay, fine. So similarly here you can see that now I want to see which line it has taken, right? So just I have tried with that, then I could see that this line is being considered by the algo, right? So this is what we can do. Similarly, I have done for with multiple variables, right? Area, bedroom, age, and then price, right? So here what I have done is it's a small example only just to make you to understand. Okay, so here NaN, which means there is one missing value, right? There is one missing value in my data set, in my CSV file. That's why it is saying that there is a NaN. So how do we fix this NaN? We have to replace it with a median value. So I'm writing, right, this I have, my data frame name is AP. So that's why AP dot bedroom, I'm trying to find out the median value of it, and it is giving it as 3.5. So that what I'm doing, can I write it as 3.5 in this case? Can I fill with that median in this case? Yes. Okay. So roughly we cannot replace it with the median because 3.5 is about, we are talking about bedroom. Can the number of bedrooms be 3.5? Yeah, exactly. Right. So do you understand my point? So just like that, we won't be able to, just like that, we won't be able to do with the median, right? So what I'm doing, just I'm trying to make it into an integer, and then I'm replacing it with the number 3, right? Now the step is going to be the same, right? Reg equal to linear regression, and then I'm trying to fit with that, right? So x-axis, and this is going to be the y-axis, and then I'm trying to get the coefficients of this. So in this case, we will be getting 3 coefficients, right? Because there are 3 variables. So I'm getting 3 coefficients, and I'm trying to get intercept of this. And then in case if I want to predict the value of this, I can try this way and get to know the value of it. It is a very simple algorithm for a simple data, just for the understanding. Is this point clear to you? Till now, is it fine? Yes, fine. So now let's look into a little big data set with some miscellaneous values. Okay. Because those are the challenges we will be facing when we deal with a data set. Okay, so those challenges we will be facing whenever we deal with a big data set, right? So this is a very good data set with missing values. So that's the reason I have taken this. From next session onwards, I am going to choose only the data sets that is related to marketing, operations, and finance, right? So those kind of use cases we will be seeing in the next classes. So what I have done, let me explain to you. I have imported the libraries NumPy, Pandas, Matplotlib, Seaborn. So these 4 we know already. And I have written from sklearn.linear_model import linear regression. And I have written another one, train test split. See, just be careful, otherwise you will not be able to understand any of the algorithms, because this is going to be the basic for you. Okay, so whenever we do machine learning model, train test split is very important, right? So that we are going to do right now. Partitioning, I think you must have seen that in that slide, first part, like data preparation, you must have seen partitioning, right? So this is very important. This is very important. This is default in all the machine learning models. Import train underscore test underscore split. Okay, fine. Okay, libraries are being imported. Then what I'm doing, I'm trying to, okay, let me execute it. So then what I'm trying to do, I want to read my file, right? So I have stored it in autompg.csv. This is available in your LMS. Okay, you can go to online repository and check for the data, right? So there are so many CSV files you can take and work on that, right? Okay, so the next step, what did I say? We should try to understand about the variables. We should also know the problem statement, right? So here the problem statement is like how is MPG related with the cylinders, displacement, horsepower, weight, acceleration, or so that is the basic ideology of this problem statement. How does MPG related to all the other parameters? Right? MPG, you know the meaning, right? Miles per gallon, right? So how does it related to all the other variables? That is what we are going to see, right? Okay. Now in this case, let's study the variables MPG. So MPG is numerical, and cylinders. So here we should be very much careful. One more point, it is not necessary that the target variable is always present at the last. But if you take any data set from Kaggle, most of the times it is present at the last column. So people have an understanding that it is always present at the last column. It is not like that. From the problem statement, we should be able to identify whether it is a dependent variable or independent variable. In our case, I said that we are going to study how MPG is related to all the other parameters. So MPG is dependent upon the other parameters. So that's why this MPG is going to be the dependent variable, right? And cylinders, it is going to be the integer, I guess. And displacement is float, horsepower, integer, weight, acceleration, model year, origin 11111. So what is that origin? Okay, so from SMEs I came to know that in origin of car they have given about American, European, Asia. So they have given it as they have marked it as 1, 2, or 3. Can I work like this? And then car name is also given here. Now tell me, okay, this is presented to you. What will you do? You are asked to study the relationship between MPG and the other parameters, right? You should also know which are the important parameters which can be dropped, and can you run this one as such? Any answer from your end? Can we run like this? If I make a model with this data, what challenges I may be facing? This is text data, first of all, right? This is text data. The machine is not able to understand the textual data. So this will be failed. And do you think this car name is important or not? No. So car name is not important. So there you can take a call there whether we are going to consider the variables or not. The data collection team will be working like this, right? Sometimes they may bring the unwanted variables also. So there you can take a call that it could be deleted, right? We can drop this car name, and origin also could be deleted. But since I wanted to show you like how these kind of variables can be treated, that's the reason I have kept it as such. If I have this as 1, 2, or 3, and if I make it as a model, what we may expect is like this also may be considered as a number, but it is not a number basically, right? It is not a number. It actually says 1 belongs to American, 2 belongs to European. So that is what it is telling us. So if you run as such, it may bring us a problem. So what I am doing is, so C data is the data frame name, a data frame. So I am dropping car name. Whenever we drop it, you remember X is equal to 1, which means car name column should be dropped. X is equal to 1 means column, right? So car name, this has to be dropped. And then what I'm taking a call over there, I want to replace 1 with America, 2 with Europe, 3 with Asia, because that is how it is being given over here. So that is the part I'm doing now. And then I'm checking my data. Now, when I check it, I'm coming to know that, yeah, it's getting changed, right? Now I can see it over here. Now, again, the challenge is that the machine may not be able to understand the categorical data. So what we have to do, we have to create dummy variables for that. What is the meaning of dummy variables? The dummy variables can be created with the help of pandas, that is pd.get_dummies. So this is data frame. And where do I want to dummify the data? In the column of origin. So origin column will get dummified. So what's happening over here? Wherever it is America, only, so now you can see that 3 new columns are being introduced now. Can you see that? Origin America, origin America, origin Asia, origin Europe. You can see that 100, 100, right? So wherever it is America, America will be 1, remaining 2 will be 0. Whenever it is Asia, Asia will be 1 and remaining 2 will be 0. Now in this case, the machine will be able to make a model. This is how we have to deal with the categorical data. Is this point clear to you? Just what you should know is the machine cannot understand categorical data. So we have to dummify the data.